Okay, guys, this is lesson one of the Sun and Earth Moon system. So, this is a continuation, really, of astronomy that we looked at in first year. We want to understand the relationship of these three celestial bodies in our part of the solar system, because there must be something special about the way that these celestial bodies interact that has allowed life to exist on our planet. So we want to kind of bear that in mind. We want to figure out kind of what conditions are preset on Earth that have allowed life to evolve. Okay. Now, there's a little bit of revision in this, in that we looked at the definitions here of planets, stars, and moons all the way back in first year. But today we're going to recap all of that and maybe have a look here at one thing that we should all find quite interesting, which is how do these celestial bodies stay in orbit around each other? And it has an awful lot to do with two different things that we'll be looking at today. It has to do with gravity, and it also has to do with something called momentum. Okay, so that's our goals here today on this particular chapter. So, in relation to this, the first thing, anyways, is testing your knowledge. What facts should you know here about the Sun and Earth Moon system? Now, you might take out a pen and write down just maybe 4 or 5 facts that you know about the Sun and Earth Moon system before you even start. Okay, so some facts here you might know, for example, is that our Sun is an example of a star. Okay, our Sun could be called a yellow dwarf star. You might know that the sun, of course, gives out heat and light. You might know other things as well, like, for example, the definition of a star, which is a ball of gas that gives out heat and light in the form of radiation. Okay, those are all things you might have mentioned here. Now, there's other things, of course, and I want you to create a comprehensive list for this to really try to narrow down what do you actually know about this. Okay, so three definitions here for you that we really should ought to know really before we look at this chapter is, as I said, the definition of a star. Star there, like, what is the gas we're talking about? So what gas is found in our sun primarily? And it would be a gas called hydrogen, and there's also another gas there as well, which is helium. So, hydrogen, you might know a little bit about it, that it is highly flammable. It explodes, so it is explosive. And this kind of makes sense when you think about that. There's this kind of source of fuel, really, for the sun that's keeping it going over a long period of time. When we talk about a planet, you might remember all the ways back in first year when we looked at the definition of this, we said it's a celestial body, which means it's found outside of our Earth's atmosphere. We said that it orbits a star. So that means that it creates a revolution around, for example, like our sun. Now, each solar system, remember, has its own star, so the planets will orbit their own star. And one thing that's fundamental here in defining a planet is we say that it has cleared its orbit. And what that really means, of course, is that it has, under the force of gravity, pulled in all of these asteroids, comets, we'll say meteors, in its orbit. So whatever kind of path that the planet follows in its movement around the sun, there's actually no kind of objects in its way, because in its history over millions and millions of years, the gravitational pull of that planet has pulled all of those objects into it. And over time, under the force of gravity, because we have a force of gravity that pulling everything into the center of the planet, it creates this kind of globe or spherical like structure. Okay, so there's an awful lot in there, that definition there that's packed in to try to understand what this all means. In relation to a moon, we know that a moon is actually called a natural satellite of a planet. So it basically means that it orbits a planet. It doesn't orbit the sun, it orbits a planet. Okay, and again, so moons must be smaller than the planet itself. They be aware that some planets have no moons. So, for example, Mercury has no moon, whereas other planets have several, maybe even hundreds of moons, like we're talking about the likes of Saturn or Jupiter. Of course, we have just one moon, and when we talk about Earth, it travels, I suppose, it orbits Earth in about 29 days. Okay, so that's a full orbit, whereas for the Earth, of course, it takes maybe 365.25 days there to orbit the Sun. So, this video here will be posted to Google Classroom so you can have a look at it. But one thing here that's highlighted in this video is a comparison of um, the sun or the Earth rather to a spinning top. Okay, so we can think about the Earth as a spinning top when we picture its orbit around the Sun. Now this will become important, particularly when we start studying the seasons in the next chapter or the next rather lesson. So I said our focus for today is looking at gravity and momentum, and we're going to continue with that, trying to understand here how gravity influences our universe. There's a bit of a joke up here. I don't know, will you understand it? Gravity is hilariously weak. Go ahead, raise your hand. You literally just overcame the gravitational pull of the entire Earth. So, the gravitational pull of the entire Earth, you might realize, is a factor of 10. So, we're talking about basically a gravitational pull that's drawing your body into the center of the planet. Um, when we studied forces, you might have remembered a few things you learned about gravity and that. We've talked about gravity being a force, okay, and if it's a force, it can be measured in something called newtons, okay, named after Isaac Newton, famous scientist. Another thing then is that the gravitational pull is the reason that we're not just floating about in space like you see in those that footage really of the International Space Station and maybe in space where people are just floating about. Gravity is the reason that we have our feet planted on the ground. So those are all things that we should remember. But how does it actually work? So what we know is that forces of attraction actually do exist between different objects. Okay, you can picture magnets. If you have two objects, you place them, we'll say, adjacent to each other, then there will be some sort of gravitational attraction between the two objects. Okay, naturally. Is this measurable? Yes. Does it make a difference? Usually, no. Okay, so if I have two people, for example, sitting on a bench, technically you could say there's a gravitational attraction between the two different people's bodies. Okay, this we call a gravitational pull. They are exerting a pull on each other's bodies. But for small objects, this is measurable and it makes no difference. Okay, even though there's a slight gravitational attraction between the two bodies, there is it makes no realistic difference. I mean, you're not just pulled towards another person and them towards you. Um, this is um, this is something that doesn't happen around us because the force we exert on each other is not strong enough. But when we're talking about massive objects, and I want you to picture now the celestial bodies. So, massive celestial bodies, this will make an enormous difference. Okay, so what you're talking about here is things like the stars, the moons, all of those make a massive difference because they are so huge. So, one thing we can say here is that the bigger the mass of a celestial body, the bigger um, the gravitational pull of that celestial body. So, in our solar system, you might realize we have the sun followed by 8 different planets. And all of these planets have different masses. And that means that, I suppose effectively we'll call that weight. Like you can picture weight, like an enormous mass here in space. The sun has the largest mass, and this means it has the largest gravitational pull. So it creates a large gravitational pull on all the other planets. So it's basically pulling, and it's the stronger pull of all of these planets, it pulling all these planets in towards the sun. Okay, if you look at the gravitational pull and see the relationship here between mass and gravity, what do you see? Okay, look at the numbers. We have 1.024 times 10 to the power of 26, which is an enormous mass. It has a gravitational pull or gravity of 11.15. We have the Earth, which has a mass of 5.972 times 10 to the 24, which again has a gravitational pull of 9.87. Remember, we said it's a factor of 10. So actually, when we have a factor of 10, really what we're doing there is we're rounding it to 10. And also then the final one here, which is 1.898 times 10 to the power of 27. So which one of those has the greatest gravity? If you look here, you can see this has 24.79. But why? Because if you look at the indice here, so remember an indice is something like, so if I had 10 to the power of 3, that's really 10 by 10 by 10, which is 1,000. So the bigger the indice here, in this context, it means the bigger the planet. Okay, so the biggest planet here is planet 3, and it also has the biggest gravity. The second biggest planet here, you can see, has 10 to the power of 26 compared to 10 to the power of 24. This is the second biggest planet, and lo and behold, it has the second biggest gravity. So Earth is the planet here, third planet here, which has the least gravity of these different three planets. So what do we want you to take from this? But there is a relationship between mass and gravity. The greater the mass, the greater the gravitational pull of that planet. Okay? So how does this work in effect? Because remember, if I come back to what I was saying, the sun exerts a gravitational pull on all of the 8 planets, and effectively what it's doing is it is pulling them towards the sun. Okay? Now, the question is though, why aren't they pulled towards the sun? Why are they still in orbit? And this will be something we'll be coming on to next. But in order to understand this, we must understand as well the factor of distance. So technically, the greater the distance between two different objects, the less the gravitational force on them. Picture magnets, okay? So the closer you bring the magnet to another magnet, the greater the force of attraction or repulsion. If you have magnets which are very far from each other, even though they might be in the same room, they mightn't actually have any effect on each other, okay? So yes, the sun has a massive gravitational pull, but it also its pull on all of these planets decreases the further out from the sun you get. So we could make a hypothesis here and say the gravitational pull on the 8th planet, so my very evil mother just swatted uncle's nose, it's Neptune. So the gravitational pull of the sun on Neptune should be the least, okay, of all the planets, because with distance it decreases. Right. So, as I was saying, how do planets actually stay in orbit? Why, if the sun is pulling them in, what's to stop them from just falling into the sun? Well, there's two things to bear in mind here, right? If you look here at this diagram, can you explain what's happening? This large celestial body could represent, for example, the sun, okay? And this satellite here could represent, for example, a planet like Earth. What we should recognize here is there's two arrows. This arrow here, which is basically an arrow pointing towards the sun, is basically a situation where the satellite is falling into the sun. Okay, the Earth is falling into the sun. But we've also got an arrow here, which is kind of taking it around this orbit. So this is an orbit around the sun. So what you should recognize is that these two arrows here are roughly the same in size. Okay, in other words, these arrows represent forces. They are force diagrams. Okay? And one hypothesis you might make about this is that the forces acting on the planet are the same. So this force pulling it into the sun and this force pushing it around its orbit are exactly the same. And that is because of something called balanced forces. Okay, if two forces are balanced, it means that an object will stay in motion or it won't move at all. So if an object was already in motion, then it will stay in that exact motion. It won't change its trajectory. I have a few bits of information here on the right that we want to read through and see can we understand. And let's read it together. The first thing, there's two reasons here, two main reasons here I want you to remember why planets stay in orbit. The first thing we could say here is that gravity. Gravity is causing a pull on smaller. Gravity from larger celestial bodies, rather, is causing a pull on smaller celestial bodies, which is drawing them in towards the sun. If there was no other forces, if you could ignore this arrow, if there were no other forces, this satellite here would fall directly into the sun, okay, into the larger celestial body. But that's not the case, is it? Because there is this arrow, and this arrow here represents momentum. This comes from someone called Newton, okay? Remember Isaac Newton. Newton's law states that objects in motion will tend to stay in motion unless acted upon by an external force. So even though that this satellite is falling into the sun, the force that's pushing it around in its orbit is enough to balance out this basically pulling effect into the sun. So it never actually falls into the sun because this force is pushing it. It's equal and it's pushing it around the orbit instead. So if you didn't have those two forces acting together, if you didn't have the gravity, well then the planet just could just float away into space and it could be gone. Okay, it could be gone into the universe. So you need the force of gravity to kind of keep this pulling into the sun effect. But the momentum, this pushing effect, where it pushes it around the sun, is important to stop it from falling into the sun. So these forces we know over long periods of time have been balanced. Okay, but if they were unbalanced, the reason they would be unbalanced, if they were unbalanced, then life on Earth could not exist. If we're talking about the satellite being Earth, because what would likely happen is that if the force of gravity was too strong, if it changed somehow, then we would be pulled into the sun and kaboom. Okay. The reason that forces of momentum are not changing, by the way, guys, is because remember we're dealing with space. So in space, there's no friction, okay, which is gonna mean that there is no slowing down of the satellite in this case. So therefore, the forces are balanced, and the satellite will continue in orbit over and over and over, and it repeats its revolutions nonstop. Right, there are a few questions here that will be put up on Google Classroom, and you are to answer them based on this video.